basically this is studies about some way to improve the performance of large-scale k-nearest neighbor queries for some use cases. So the KNN is for the k-nearest neighbor query. It's to find the k which is the equal greater than 1 nearest neighbors of an object or a location. It is actually one of the most frequently performed database query. Normally it's spatial, but not necessarily a spatial query. For a single one-off k-nearest neighbor query, generally will be done by utilizing some appropriate indices, and in general, it's a solved problem. So the question is whether there's still any room for improvement, and our answer is yes for certain use cases. So the k-nearest neighbor query, the criteria for it is, there are two criteria here. One is you need to find at least k data points, and also the second one is you have to ensure no other data points closer than the above k points. So a key issue here is to decide an appropriate range of search, which will retrieve m, which will be equal or greater than k nearest points, and also limits m minus k points by distance comparison. So the computational costs involved here includes the retrieval of the endpoints from database and the distance comparison, which will, the number of the comparisons will depend on the value of m. So potentially there could be a trade-off between the point retrieval and the distance comparison. Okay, there are many ways to find the nearest neighbors. I mentioned earlier, you can use some kind of spatial indices like R-tree to do it. And here we just a very brief introduction on the way to do it using the linear triangulation. So in this case, we use the data points both as locations, and we will find the k nearest other location for giving example. For the location P0, we can find the connected locations P1, P2, P3, P4, P5, and P6, which are connected to P0 by a delineated triangle edge. So from these connected locations, we will find the newly connected locations further outwards, like P7, P8, for example. And then we will update the k-nearest locations to P0. We will stop when the search will find no new location closer than the current k's nearest neighbor. So by this way, we can find the k nearest neighbors for a certain location. There is some operations we can make about the k nearest neighbors in proximity. Here the figure A is given a query location Q0, and we, for example, for k equals to 6, the 6 near the neighbors, which will be contained in the circle CP with a radius RP centered at Q0. And now we have a new query location Q, which is close to Q0 with a distance dpq. The observation we can make is the circle CQ centered at Q with a radius RQ equals to RP plus DPQ will contains all the new 6 nearest neighbors for Q0. And therefore, if you use this RQ as a search range, it will guarantee the first criterion A for the k nearest neighbor will be met. If there are more points, other points inside the CQ other than the 6 one for 6 we found already, so we can do some distance comparison to decide the final k for the new query Q. So that's an observation made by some researchers previously. Now we consider the query location in general position, given the query location Q1 here, which is within the distance Q1 to Q0 is smaller than the dpq max distance, arbitrary distance. So the query location Q1 is inside of the circle dashed circle centered at the Q0 and distant with radius d PQ max. So what we can see is the circle CP max, which has centered at the Q0 with a radius R max equals to RP plus 2 times the distance dpq max, which will contains the k-nearest neighbor for any q1 inside the dashed circle. So in that case, if we know the RP and we knew the dpq max, and we can use this to retrieve a set of points which will be used to find the k-nearest neighbors for any q1 inside this circle. So the computational cost here involves you retrieve all points in that CP max. We need to do that only once. And then for each Q1, we need to make some distance comparisons. That will depend on the number of queries. So compared to the conventional approach, only one retrieve operation for all queries. So the more queries, there will be greater saving in terms of the data retrieval. Of course, we need the actual cost, which will be an actual distance comparison for each query. So overall saving can be achieved if we make sufficient number of queries. Here is a very rather oversimplified cost model. For single queries, we assume we have a fixed cost of 4 units per query from database, which involves the database access and the server-side distance comparison. And if we use the just mentioned retrieve plus reuse approach, we assume 10 units for initial retrieve from the database because it's 10 because we need to retrieve more points. And then afterwards, for 2 units for each subsequent in-memory query on the client side. So you can see the curve. This will be the kind of conventional approach. So initially it's very low, but it increase rapidly when the number of queries are made increasing. And for the new method, it will be more like this. You have an initial overhead, but then subsequently, for each query, the cost will be much lower. So when you reach a certain point, you have all saving in terms of the running cost. So to make use of these ideas in application, we just put a kind of application framework for its purpose, which we would do some data pre-process on the data set, which will be we wanted to perform k-nearest query on. So we just assume for k2 from 1 to 6. We will generate a set of seed locations, and they will create a space partition for the seed locations, where noise diagram is a very convenient one. And for each of the seed locations S, we will find the distance to the case from 1 to k nearest the neighbors. And then finding the distance to the furthest point in this partition polygon. In this case, here will be the furthest point in this partition polygon for this seed location. And we will store these RP, I will store these values for each k and up to the biggest k you want to support. So in this case, it will be k equals from 1 to until to 6. So we will have 6 distances of is saved. We have this maximum distance inside the partition polygon saved. And then subsequently, we can perform query. If, for example, if you have using this polygon to query, if we know all the query location beforehand, we can then use this polygon to retrieve all the query locations, and then subsequently we use this the corresponding dpq max and the RP to retrieve the data points there only once. And we can then, for each of the query locations, we use this retrieve the data on the client side to calculate the k-nearest neighbors for each of the points. It's a kind of first use case. This is actually a question I think from one of my colleagues, which actually gave me some stimulation on thinking about this problem. So in the nearest schools, the problem is for each of the about 29 million Greater Britain addresses, we find the 6 nearest schools from among the 24K schools. So the solutions will use the school as a data point as well as the city location for generating the query partitions. These brown diamonds are schools. And the address points will be the query locations here, tiny blue dots. So we'll batch perform the process all queries should inside the same partition polygon with cell. In this case, this is an example. This radius will be the RP for p k equals to 6 plus the 2 times the D max for this partition. Therefore, we use this circle as a search range to retrieve all the schools just once. And then for any of these queries inside is we can then compute the 6 nearest schools for the second use case will be kind of so you will find the nearest restaurants on move. The problem is to dynamically update the nearest 5 restaurants, for example, for mobile user. The solution will be using the restaurants as data points as well as the seed locations for the partitions. We use a trajectory of the users as query points. Here's when the trajectory into one of the partitions will perform one of the data retrieval, and then we can just use a dynamic pointing polygon test, update the nearest restaurants from that one retrieved data. So there are two technical issues for this method. One is we have a large data point set, so it's very convenient to use data points as the city locations to create the partitions. But the problems, it has to be very small. In our previous cases, the schools restaurants are relatively small, but in some cases, the data point set could be very large. For example, if you want to deal with all the lampposts in the UK, so that's kind of multi-million of it. So it's not very feasible to create a partition directly. In that case, we need some sample hierarchy of one or more levels to do it. We will then apply the method for the small data point side to each of the sampled regions. So more details can be found in our abstract. So the other issue is we need to restricting the size of partition polygons. The problem we mentioned earlier is to create a linear diagram. The issue is it will be often very large on the dataset boundary, so which will result in a very large DPQ max value. So therefore, you will retrieve a lot of the candidate points from the database, and that's quite undesirable. So the solution to it is whether either we can use some natural boundaries as a coastline to clip it. The problem with your original coastline is will be too many vortices will slow down the query point retrieval. So normally we can have a simplified version. But the simplified is it has to be one side. It used to be, for example, here is an example of the user grid-based simplified coastline representation, which actually all fall inside of the sea. So in that case, you guarantee all the lines will be covered. Other way, you will be use a concave hull to provide an efficient alternative. But in that case, you'll be very careful about the parameter values. Otherwise, you will generate some issue of the gaps here. So we did some experiment, and the sample data is the source data points. We want to make queries 23,855 schools in Great Britain. And the query points will be nearly 29 million GB addresses. The implementation is based on Java plus a local PostGIS server connected with JDBC running on a laptop. So the result we can see rather nearly about 10 times improvement. So this result is just a summary. So the 2D Max is the method presented here. We run the full data, run it on the full data set, and for every 1,000 addresses, it requires about 3.22 seconds. If we do in individual queries, if we just run the normal queries for each address, where is not be 19.43 seconds. If we just use the SQL directly, it will be even slower. So that's basically the summary results from this study. Here is a couple of points we want to discuss. So this study, in essence, is an attempt to extract a balance between two types of computational cost to achieve some kind of O or gain. So in this case, retrieving data from database is very expensive. So if we can do more reuse of the retrieved data, we improve the performance. But of course, there is a trade-off here. There will be a large redundancy in retrieved data. You have to do more actual distance comparison. In some cases, especially high-dimensional data, the distance comparison itself is going to be expensive. So whether you can achieve kind of to the trade-off will turn into a kind of net gain. It depends on the application as well as software and hardware platforms. There are also some similar applications actually following this kind of idea. For example, one example is the incremental construction of the linear triangulation using a hierarchical space filling order, which will retrieve a small increase in the edge flips for the reduction of triangulation walk distance for point locations. In that case, if you tune the parameters carefully, it can achieve all near linear time complexity. And we believe potentially more application might be done following this kind of approach to have more improvements in terms of performance. Okay, that's for me. Thank you.
Thank you very much. Thank you very much, Sheng, for your talk. Are there any questions from the audience? Okay, we have one from Anna Basiri. Can you comment on how this may work if data have the third component Z or T? So adding a temporal or third dimensional component, or I guess both.
Sorry, just a moment. Can
Sure.
you just repeat the question? Sorry.
So Anna asks, can you comment on how your approach, might work if the data, instead of being bidimensional, have a third component, which might be altitude or temporal, or I guess both?
I believe in theory you can apply it to higher dimensional data, but as I mentioned earlier, for when the dimensionality goes up, the cost of distance computation will increase quickly. So in that case, what the trade-off will become, I'm not quite sure about it. Maybe you have to adapt to some kind of simpler distance, for example, not a genuine geometric distance, rather Manhattan distance, that kind of things. So you turn the computation into comparison. In that case, maybe speed things up a bit, so gain a bit more. So it's not an additional trade-off. You may retrieve a bit more points, but the distance computation is much simpler.
Thank you. I have another question from Phil, who asks, how long did it take to make the triangles layer for schools Great Britain vision trial?
Oh, that's I think a few seconds. Not fully, because only about 20 some thousand some schools, so it's not a pretty small data set to do the linear triangulation.
I have maybe a question that is kind of related to what Phil was asking. You clearly have an example in which is what as far as I understand, brought you to this problem. You have an example where the kind of data set that you're using seems to be fairly static. The number of schools in the UK don't increase maybe annually, but definitely not daily, and the same applies to the postcodes. Also, what is the trade-off when you have more dynamic data? So maybe you have I don't know, events that comes up every few minutes, and then you have changing data set. Would that still would the trade-off be feasible?
That's a very good question. I would think its method itself is more static
Mm.
rather than dynamic because you have new data points into the play. Then you actually nearest neighbors for all those seed locations will be changing. In that case, it's always pre-computed result no longer relevant. So you have to update that as well. So I don't think that will be there's an easy way to handle this kind of dynamic situation directly using this method. So that's what I say is you have to be feasible and kind of relevant use cases if you get some gain from it.